Hey guys, welcome back to chapter 17. So I'm going to pull a fast one on you in this video. So before we were looking at solving for the pH of a buffer solution, we had a four-step process, right? The balanced equation, set up an ice table, solve for hydronium, determine pH. Well, the good news is there's actually a shortcut to doing those problems that cuts down the number of steps dramatically. So I'm going to introduce a new equation to you guys today. You can go ahead and use this one from now on. So I'm going to introduce a new equation to you guys today and show you how to use it, show you how it makes your life easier. So this is for calculating the pH of a buffer solution. The equation is called the Henderson-Hasselbach Equation. So the equation calculates the pH from the pKa and the initial concentrations of weak acid and the conjugate base, or weak base and conjugate acid, okay? So calculates the pH. That's the ultimate goal in these problems anyway. So we're going to set up our equation as such. pH equals pKa. So that's something new that they're introducing here. So up until now, I've given you Ka values. So for example, Ka is 1.8 times 10 to the negative fifth. Okay, so just an example of a Ka value. pKa is going to be very similar to how we determine pH. So remember, pH equals negative log of the hydronium concentration. Well, pKa is going to be the negative log of Ka. So literally, if I want to find the pKa, I'm going to take negative log of 1.8 times 10 to the negative fifth. So pKa equals, so negative log of 1.8 times 10 to the negative fifth. So pKa is 4.74. Okay. So pKa is going to be the value that you see in this equation. And then this is just teaching you how to get to pKa if it doesn't give it to you, if it only gives you Ka. All right, so calculating pH from pKa, initial concentrations of weak acid and base. So those are the numbers that are given in the problem. Okay. So as long as x is small is valid, we can use the Henderson-Hasselbach equation. And you can go ahead and assume from here on out that x is small is valid. So here's our equation. pH equals pKa plus the log of base over acid. So base is going to be that salt, the conjugate base, so the concentration would go there. And the weak acid is going to be the concentration that goes on the bottom. Okay, so this is going to cut out the ice table. This is going to cut out solving for hydronium. And you're just going to be able to go straight from the problem, write the equation, determine the pH. So we're cutting out a bunch of the steps here. Okay, so let's dive into an example. All right, what is the pH of a 0.1 molar acetic acid? Oh, sorry, let me redo that. The pH of 0.1 molar acetic acid is 2.89. Calculate the pH of a solution prepared by mixing 0.25 molar acetic acid and 0.38 molar sodium acetate. So it's giving us the pH of acetic acid by itself, but then it's asking us to calculate the pH of the buffer. So that's what we're going to do. So first step still, we want to write the balanced chemical equation. So that way we know what is the base and what is the acid. We can see this on our paper. So I'm going to do it in a blue so it kind of stands out. So acetic acid is C2H3O2. It's going to react with water. Acetic acid is the acid, so it's the proton donor. So it's going to be left just as the acetate ion. And then we're going to have hydronium. So this guy right here says 0.38 molar sodium acetate. For some students, it helps to write sodium acetate on this side. So you could write acetate ion, or you could write sodium acetate as the salt. It really doesn't matter which one that you write, because remember, this is going to dissociate into sodium and acetate, and sodium doesn't affect the pH. So whichever version works better for your brain, do that. Okay. So to calculate the pH, we're going to fill in first the pKa. So we're given the Ka. So remember, pKa is just negative log of 1.8 times 10 to the negative fifth. So pKa equals, I think this is the one I just did. So negative log of 1.8 times 10 to the negative fifth. So pKa is 4.74. Okay. So let's start plugging and chugging. pH equals pKa 4.74 plus the log. Okay. Now we've got to determine what's the base and what's the acid. So acid, I think, is a little bit easier in this case because it says, let's come over here. It says acetic acid. So acetic acid is going to be our acid. So that's going to be the concentration that goes on the bottom. And then the 0.38 molar sodium acetate. So that's going to be the conjugate base. So the base goes on top, so 0.38. Okay. So to solve this, pH equals, I'm going to leave that 4.74 alone. Whoops. Plus log. I'm going to go ahead and divide those two numbers. So 0.38 divided by 0.25. So that's 1.52. So then I'm just going to type into my calculator log of 1.52. pH equals 4.74 plus 0.18. So pH is 4.74 plus 0.18, 4.92. Okay. So that's calculating the pH of a buffer using the Henderson-Hasselbach equation. Does this make sense? So that's why they gave us this little piece of information in the beginning. So acetic acid by itself has a pH of 2.89. Does it make sense that an acetic acid buffer has a pH of 4.92? Yeah, that makes sense. We added some of the conjugate base, therefore that pH should rise a little bit. So that's why I gave you that information in the beginning, is just to give you kind of a reference point of, does this make sense? Okay. Hope you guys found this helpful.